Right, boys, here's the solutions to the written section of this paper. Part A said between 1 and 0 evaluate 1 minus x to the power of a half with respect to x. So, well, straight away I'm going to write down my bracket, which is 1 minus x, and then I'm going to add 1 to the power, 3 over 2. And, well, I've got to take into account my power now, so if I've got to look for the reciprocal of it. So out here I'm going to put 2 over 3. And because that x is negative, I need to have a negative out the front as well. And again, if I asked you to differentiate this, what would we find? Well, I'd have, if I had negative 2 over 3, 1 minus x, 3 over 2, then the derivative of that, d over dx, will be what? Negative 2 over 3 times 3 over 2 times the derivative of the bracket. We go power, then our derivative, which is negative 1, then my bracket, and I'd end up with a half because I dropped my power. Well, I've got negative and negative, so I end up with a positive. 3 over 2 times 2 over 3 is 1. I end up with 1 minus x through the half. So boys, that's just a reverse quotient rule, a reverse chain rule there, and we end up evaluating it here between 1 and 0. Again, so whatever is going to appear here needs to give our original. So I'm going to have 2 over 3 here to multiply that 3 over 2 to give me my original 1, which is at the front here. So if I go and substitute in there, well, my first one will be 1. Of what? 2 over 3 outside of 1 minus 1 to the power of 3 over 2 minus 1 minus 0 all to the power of 3 on 2. Okay, well, what do I get? First part there is simply just 0, so that goes. So I end up with negative 2 over 3 outside of negative 1, because of course 1 minus 0 all to the power of 3 on 2 is just 1. And my answer is 2 over 3. So a lot of you ending up with negative answers there. Remember, you've got to take out that negative out here because our coefficient of x is negative. Alright, second one, we've got to differentiate this. Now, notation is very key. You could say let y equal that, or you could just use a d on dx notation, not dy dx or y dash, because it's not defined as y. So first of all, I'm going to rewrite that as x to the negative a half. So I'm going to write down my power, which was negative a half, multiplied by x. Well, I subtract 1 from the power, so it becomes negative 3 on 2. And that answer is correct and acceptable, but I'd prefer to see it written in index form, which is a half times 1 over x to the 3 on 2, which is negative 1 over 2 times, well, x to the 3 on 2 is the root of x cubed. Again, that's better. It's a better answer, and if you're asked to simplify or show that it's that's where we're looking, but technically that one is correct as well. Alright, part 3 is a limits question. We've got to evaluate this limit here. The limit as x approaches 5 of x cubed minus 125 over x minus 5. And of course, what we've got here, we can't just substitute in 5 because we'll end up with 0 over 0. We can't divide by 0. So what we need to do first is factor it. So it's x minus 5, and this is a difference of 2 cubes, not a perfect cubed, which becomes x squared plus 5x plus 25. Go back and have a look at your prelim notes if we need to recall how to factor a cubic. And then, of course, these two go. I'm left with x squared plus 5x plus 25, which gives me, well, now I can substitute in because I'm not disobeying any mathematical law. So now I have 5 squared plus 5 times 5 plus 25, all positive, which is 75. Okay. Alright, we had to evaluate this. 14 k equals 3. 5 minus 6k. Alright, so remember, this just means sum of. Now, sigma here just means sum of. So this is an AP. And my suggestion here is you could go and find the difference and the first term and the number of terms. I think it's probably easy just to go the first and the last term. We get the first term by substituting k equals 3. And then the last term by substituting k equals 14. So my first term will be 5 minus 6 times 3, which is negative 13. And my last term there will be 5 minus 6 times 14, which is negative 79. Okay, now all we need to do now is perform our sum, which is n over 2. I'm going to leave that for a second. Minus 13 plus minus 79. That plus is redundant, so we'll get rid of that. Now, how many terms are there here? Remember, the trick last week was if you just go 14 minus 3 is 11, you're actually missing a term. Count them up. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Well, there's 12 of them. Okay. So you can subtract the two numbers there, 14 minus 3, and then add 1, or however is helpful for you. So our sum there is just 6 multiplied by negative 92, which is negative 552. Okay, we're comfortable. I hope we're comfortable with this next part. Because this is common. It should be our bread and butter. We've got y equals x cubed minus 6x plus 1. So y dash, or dy dx, is 3x squared minus 6. Again, that notation, boys, don't just say equals equals equals. You've got to define what it's equal to. So that's our first derivative. We don't need our second derivative. When x equals 1, I'm going to substitute back into my original and find that y equals 1 minus 6 plus 1, which is negative 4. And when x equals 1, my first derivative equals 3 minus 6, which is negative 3. Alright, that means the gradient of my tangent equals negative 3. So the gradient of my normal is going to be 1 on 3. Again, negative reciprocal. And what do well, I've got my coordinates of my point, and I've got my gradient, so I end up with point gradient formula. Y minus minus 4 equals 1 on 3 outside of x minus 1. And that's y plus 4 equals a third x minus 1. I'm going to multiply by 3 and put this in general form, so I end up with 3y plus 12 equals x minus 1. Simply by multiplying each side by 3, and I end up with x minus 3y minus 13 equals 0. Whatever form you had it in was fine because it doesn't specify. But it does need to be the normal, not the tangent. Alright boys, the last one here had a few people asking questions, so I'm going to make an attempt to draw this sketch. Okay, something like that. Okay, and we had A here, we had B, and we had C. Alright, well, what we notice is that you've got a horizontal line there. And what you'll notice is it's both a point of inflection, as in it turns, and it's also changing concavity. So here we're down, and here we are up. Okay, so around there's been both a change in concavity as well as a turning point. So what we say is for part 1 there, A, in fact I'll do that up here. Pardon me. We say A is a horizontal point of inflection. So simply to say it's a turning point or a stationary point is not acceptable. It's horizontal, which means a turn, but it's also a point of inflection, so it has both properties. And the second part here, you're asked to draw the gradient function, or sketch a possible gradient function for y equals fx. Well, again, if I've got a horizontal point of inflection, it means it's both a turn and it's a point of inflection. We know a point of inflection here on our function fx is going to be a root down here, but it's both a root and a turn, so it'll be something like this. And then b is just a normal point of inflection, so that's going to be a turn, something like this. And then this here c is a turning point, which is going to be represented by a root on the gradient function. So that's something like this. Okay, so again, we've got two things going on here at A. We have the turn at B, and then at C we have the root. Okay, boys, go back and have a look at the notes from the start of term 4 if you're struggling with that one, or I'm happy to answer any more questions. Hope this has helped, boys.